Hello, everybody. My name is Marko Komac, and I'm your host and anchor for today's second webinar that Project CEEGS is organizing. The topic of today's webinar is going to be thermodynamic modeling. And I guess those of you who have registered and are following this webinar are quite interested in the topic that we're going to cover today because they are very interesting ones. We have 1 hour for our disposal. As you could hear, the webinar is being recorded, so it's going to be also available online afterwards whenever you wish to rewatch it, or if somebody else that could not join us today wish to watch it later on. To shorten my long and boring introduction, because I'm just representing the overall things, I would slightly conclude here just to say that we have today five presentations. The last one is going to be joined in one presentation, and it's going to be presented by two colleagues from HZDR. And then in the middle part, we have three presentations, and as introduction, to give you the overbroad view on the CEEGS project, our coordinator, Ricardo Cartejei, the acknowledged professor at the University of Seville, he's going to present you what the project is all about. But before we start, I'm just going to give you a short bio on his expertise because I think they are quite important. So Ricardo is a professor at the Engineering Energy Department in Seville, its university, and he obtained his PhD in 2005. And he has more than 150 documents registered in Scopus and over 80 publications in international congresses since that time. His main research fields are related to energy storage, novel energy systems, and LCE technologies. He had participated in more than 60 projects in collaboration with industry, and he has patented 9 patents. Kudos to that, Ricardo. And he coordinates, as I already mentioned, this project, the CEEGS project, which basically talks about the transcritical CO2 energy storage possibilities that we could utilize in the future. So, Ricardo, please, the floor is yours. Pass us through the introduction of the CEEGS project. Thank you.
Okay, thank you very much, Marco. Thank you everyone for attending this webinar. Well, I will introduce in a very short, very fast way the project. The CEEGS project is a 3 years project. You can move the slide, please. It's a 3 years project in which we study a novel energy storage system that combines a Carnot battery and geological CO2 storage. It has unique characteristics regarding the capacity for energy storage. It can store energy, the concept can store energy in the way of thermal energy, but also in the way of mechanical energy with the compressed CO2 underground. The behavior underground is similar to the ones that we can expect in a compressed air energy storage, but taking advantage of using the CO2 as a working fluid. The main advantages are related to the very good characteristics as working fluid of the CO2, the capacity of a partial sequestration of the CO2 in the terrain. So it's an additional benefit that can have using it captured CO2, and also the characteristics, the thermodynamic characteristics of the CO2 also can provide benefits regarding CO2 thermosiphon effects, and also reducing injection costs and having big advantages regarding enhanced geothermal heat extraction. In this project, you can move to the next slide, please. In this project, what we are our goal in this project is to demonstrate the feasibility of the concept. So we are studying different layouts, different integration, and also analyzing the different components at this early stage technology. So we are not developing exactly the final design of the heat exchangers or turbo machinery, but we are analyzing if under the proposed cycles there are feasible turbines, feasible compressor, feasible heat exchangers that can be constructed, that can be operated, and they can be integrated in the final idea. And we are doing this analysis through modeling, that this is the objective of the webinar of today, explaining how we are dealing with them. And our focus is at all in the project in the interface between the surface components and the subsurface. As I said, it's a novel concept that integrates thermoelectric energy storage based on reversible transcritical CO2 cycles, and also have the potential for CO2 storage in geological. It's an scalable system with high performance, high capacity energy storage, as we have already demonstrated with the analysis that we have already performed in the previous 2 years of the project. The concept minimizes cost and surface impact and increases the energy storage capacity compared to the Carnot battery without the integration of the geological side. What we are going to do? We are going to develop a proof of concept for the interface, reaching a technology readiness level of 4, and we do it analyzing the integration of models for the systems, components, and with a lab demonstrator for the surface side. We will show today how are the works advancing on that. Next slide, please. Now we are in the second year of finalizing the second year, so we have 1 year ahead. At this stage, we can say that all the concept, all the analysis that we have done show that the concept is feasible, is viable, high efficiencies are expected, higher than the Carnot battery standalone, and we are having very interesting results with novel designs of the concept and showing the feasibility of the components that integrated. We expect to have at the future a second project to increase the technology readiness level towards the commercialization. Okay, that's all from my side. Okay, so no, sorry, not all, sorry, I forgot. Oh, which are the expected results and impact that we have in this project? We have 3 main blocks regarding the challenges. Challenge regarding the integration of surface and subsurface components to a system. Challenge related to the conceptual design of novel components adapted to the requirements of the cycle. And the third challenge is big block challenge is the techno-economic feasibility and impacts related. It includes also the social acceptability and the acceptance of the technology. And that's all from my side. Thank you. Now, Andres, I give the room to you.
Ricardo, thank you very much for this short overview of the project. Before I pass it on to Andres, I would just like to shortly introduce him because he's also quite a good, quite an excellent expert in the geothermal modeling. So Andres studied industrial engineering and concluded his bachelor's 5 years ago, and just last year received his PhD in energy, chemical, and environmental engineering at the University of Seville. He's also currently employed there and working as a research and development engineer in thermal engines and machines in the group that Ricardo is leading, so his Department of Energy Engineering at the same university. His main research contributions focus on sustainable energy storage using systems based on abundant and sustainable materials. He is actually the reason why we are all here, because he was the first author of the first publication in this field that we are researching further on with CEEGS. And let's say that he's one of the fathers of the CEEGS project. So thank you for that, Andres. And the next several minutes are yours. And please dive us into the numerical modeling of the CEEGS system. Please.
Okay, thank you, Marco, for the presentation. And I'm going to present now the first part of the numerical modeling. So the CEEGS technology is based on the combination of an energy storage system and the production of electrical power and CO2 storage in geological formations. As an energy system, it uses the same operation principle as a Carnot battery or reversible heat pump, in which the conversion of electrical energy to thermal energy takes place. In a first carrying phase, a heat pump cycle is used to convert electrical energy from renewable source into thermal energy, which is stored at two temperature levels, high and low. In a second discharging phase, the previously stored thermal energy is used in a power production cycle for the production of electrical energy. This provides to the system with the capability to produce flexible electrical and thermal energy at two temperature levels, covering heating and cooling applications. In addition, using CO2 as the working fluid in the energy conversion cycle allows the integration of carbon capture and storage processes. The technology employs transcritical CO2 cycles in thermal energy conversion processes. Both the heat pump cycle and the power production cycle involve a compression and expansion process, heating or cooling under supercritical condition, and a phase change. The high temperature thermal energy storage system is integrated by a sensible heat transfer with heating or cooling of CO2 under supercritical conditions. The temperature range of the CO2 in supercritical conditions allows for the use of hot water as a high temperature thermal storage system. The low temperature thermal energy storage is integrated by a latent heat transfer in the CO2 phase change. The CO2 phase change enables the integration of the water to ice phase change as a low temperature thermal storage system. These conditions of CO2 availability at high pressure levels and relatively low temperatures allow for the integration of geological CO2 storage processes. When considering a capture CO2 transport and storage processes, high pressure and low temperature conditions are compatible with both the supercritical transport and the pressure and temperature requirements for geological injection at the wellhead. Using the CEEGS system, CO2 can be conditioned for injection into underground geological formations without the need for additional energy input. By modeling of the system will depend on the processes shown below. A carrying and discharging phase, each associated with a transcritical CO2 cycle and heat transfer to high and low temperature thermal storage, and the integration of the geological process of CO2 production and injection from the underground reservoir. By integrating the geological processes into the renewable energy storage system, additional benefits are incorporated, such as a smaller geothermal gain, the lateral migration, or the residual trapping of CO2, causing that a portion of the stored CO2 to become permanently fixed. The processes involved in energy conversion depend on the modeling parameters shown in the table. Low temperature thermal storage depends on the phase change temperature. The temperature range of high temperature thermal storage depends on the output conditions on the carrying phase compressor and the discharging phase pump, which depend on the CO2 pressure on the high temperature side. The power equipment is modeled from the isentropic performance on the equipment. In addition, compressor and turbine curves have been introduced in the modeling of part load operation, as well as a step heat transfer at temperature exchange. The round-trip efficiency of the system is calculated considering that all energy stored during the carrying is used for discharging, so that the indicator only depends on the enthalpy drops in the main equipment involved in the CO2 transcritical cycles. The good integration in the temperature profiles on the heat exchange is essential to achieve a high system efficiency. In the case of low temperature thermal storage, the phase change temperature conditions, the phase change is conditioning the CO2 evaporation and condensation processes. Evaporation in the carrying phase has to be at a lower temperature than in the phase change, while condensation in the discharging phase has to be at higher pressure. The CO2 condensation process has to be a pressure that has to be higher than the evaporation pressure. In the case of the high temperature thermal storage, the temperature range is conditioned by the outlet conditions of the compressor equipment. The compressor outlet temperature is the highest temperature of the system, so the turbine inlet temperature will depend on this value and on the best or worst integration of the temperature profiles between the supercritical CO2 cycles and the thermal storage. In terms of modeling the geological processes, the conditions in the reservoir depend on the type of the reservoir, rock cavities or porous media. The depth of the reservoir and the ground conditions, such as the geothermal gradient, are conditioning the CO2 in the reservoir. CO2 injection and production processes are modeled using the adapted salt cavity model of Khaledi et al. And the wellbore floater model of Adams et al. This incorporates the simulation of heat transfer and pressure evolution, dividing the well into segments, which depends on several parameters such as diameter, depth, ground temperature, wellbore materials, or pressure losses. The numerical model offers a multitude of results and a wider range of analysis. The optimized coupling of phase change on the low temperature side, and optimized integration of the CO2 cooling and subcritical water heating and cooling. The heating and cooling applications have been analyzed, considering multi-stage heating and cooling or the phase change temperature management. An evaluation of the CO2 pressure range that maximizes the efficiency has been performed. The evaluation of pressure and temperature conditions in the carbon dioxide injection and production, or more detailed studies, such as the preliminary evaluation of the seasonal energy and CO2 geological storage, or different configurations of the cycle, adding the multi-stage compression, heat recovery, or reheating. As conclusions of this part, the numerical modeling allows the feasibility of the technology to be demonstrated both global and at the component level. At an early stage of design, the feasibility of the integrating the proposed concept is demonstrated. The numerical modeling shows that under certain conditions, heat exchanges are feasible, the evolution of the processes in the power equipment is consistent, And there are possible configurations for the carrying and discharging phase, as well as for the integration of components, achieving a high efficiency of over 60%. Now that's all for my side, and now I give the floor to my colleague Dunia, who will be in charge of presenting the next part of the Neuromolecular model. Marco.
Thank you very much for this. We will collect your questions along the presentations, but we will address them at the end of the workshop, just to let you know that if anybody has any questions or suggestions, comments, you're more than welcome. And like I said, we'll address them at the end. Now, the next speaker is going to be Dunia Benu. She comes from the Converge LDA that is affiliated to the University of Évora in Portugal. And Dunia earned her master's and PhD in petroleum and gas engineering from the University of Bourmes in Algeria. Like I said, she's currently working at Converge, and she's doing her PhD postdoctoral, research there. But previously, she was involved as an assistant professor in the Faculty of Hydrocarbons and Chemistry in Algeria. And her research focuses on reservoir engineering, specializing in CO2 storage and hydrogen projects. Dunia has expertise in flow assurance, production chemistry, optimizing oil and gas production. Her interests include CCUS, energy storage, enhanced recovery, and hydrogen storage. So very similar and related fields to what we are doing, and of course covering also these fields. She's going to pass us through the underground geological scenarios that are quite important for this technology to be implemented. So please, Dunia, the floor is yours, and give your presentation. Thank you.
Thank you, Marco. Hello, everyone. Today I will present you a part of our sixth project, which is among the geological scenarios environment. So can you please go to slide number 1? Okay. So as my colleague has mentioned earlier, that the sixth technology rely on the integration of the subsurface and surface component. So our focus is to study the section highlighted by the red cycle in the thermodynamic. So this part involves a series of CO2 injection and production phases within a geological formation to store the excess energy and retrieve it as needed. So our system consists of 2 separate wells that operate in tandem during the charge and discharge phases. The cycles include, the charge phase include the CO2 where it is injected into well A, and the discharge phase where the CO2 is produced from well A while being simultaneously injected into well B, as illustrated in the figure. So the energy cycles in our system is a short-term energy cycles with a duration of 24 hours and 6 hours for each charge and discharge cycles, followed by 6 hours of shut-in period. Next slide, please. So in this project, we have investigated various geological environments to assess the feasibility using the CO2 energy storage, as shown in the figure. The most efficient that have been seen as a candidate for the sixth technology from the technical feasibility include the porous media reservoirs and the salt cavern. However, in this presentation, we will show a case study of the porous media, which is the deep saline aquifer. This scenario of the deep saline aquifer present several advantages, such mainly is a very good candidate to manage the pressure in the subsurface and underground. Unlike the closed boundary aquifer, because the boundaries, the aquifer with closed boundaries, they also usually lead to bottom hole pressure that can increase during the plume buildup and then can lead to fractures and possibly break the cap rock. Additionally to these advantages, compared to the depleted reservoir field, the open boundary saline aquifer further can have further advantages, like because the depleted hydrocarbons are known that they contain some residual hydrocarbons or natural gas, which that can contaminate the plume, CO2 plume, and that will pose a challenge on surface facilities that are not typically designed to handle such flammable gas. Next slide, please. So in this scenario for the deep saline aquifer, which is the CO2 the initial phase of the cycle of the concept is the CO2 plume, the main stage of the CO2 plume, which is a crucial component of the system. Here the CO2 is continuously injected in the upper part of the reservoir over a sufficient long time to obtain a high level of CO2 saturation so that the energy storage cycles can start. So it's a variable that need to be optimized for each specific reservoir. Here we show the data or the parameters that are used as a base case for the flow rate injected, the time injection time, and the petrophysical parameters. So the deep saline aquifer is from a real case in Portugal, which is a smooth anticline in a siliciclastic reservoir, and the aim here is to study the effect of different reservoir parameters and geological parameters on the saturation, gas saturation, supercritical CO2 saturation around the well back producer. So maintaining this concentration is vital for the efficient surface system. So the objective is to see how this impact or how these parameters will impact the value or the gas saturation and also the water production rate in the back producer. So we have been studied some parameters such as the flow rate, the permeability, the porosity, heterogeneity, anisotropy, relative permeability, and shut-in period. I will present some results of 2 or 3 parameters that are mainly important for the output, for our output, such as the gas saturation and the water rate production. Next slide. So since we know that the water is the main impurity that compromises the CO2 purity at the wellhead, and due to the presence of residual water near the well, some water will be co-produced. Here we have a simulation for the effect of injection rate, CO2 injection rate on the gas saturation and the water rate. We did simulation to over 3 parts of the interval perforation, the top of the reservoir, the 2/3, and the full length of the perforation. So we can see that the water, as the CO2 injection rate raises the gas saturation, and also which will decrease in the water production during extraction. However, a peak saturation of approximately 76% of gas saturation for a porosity of 5%. And this saturation level do not increase further due to the presence of irreducible water in the reservoir. Also, under anisotropic condition, the gas saturation in the top third of the wellbore is slightly lower than it would be under isotropic conditions. And this also will contribute to an increase in the water production rate in the well that is back produced for the CO2. The second effect, which is the porosity and permeability effect on the 2 main parameters, next slide please, are the horizontal permeability and the vertical, which is the ratio of vertical to horizontal permeability and porosity. We can see that the permeability, we know that the permeability governs the flow of the supercritical CO2 in the reservoir, and this permeability the increase or the ratio of the permeability and the permeability ratio will influence the water production rate during the extraction. As expected, the minimum water rate corresponds to a maximum gas saturation. Also, for the porosity, it tends to have an inverse relationship with the gas saturation. Such low porosity enhances gas saturation. Also, we can conclude from this result that we can establish a range for the permeability so that the minimum water rate is produced with the maximum of gas saturation. for practical application. The last parameters that we are showing here in the study is the effect of heterogeneity. Next slide, please. So it is the parameter that affects severely the shape and the behavior of the CO2 plume during the injection. So to quantify this effect or the degree of heterogeneity, we have used the coefficient of variation, which is a metric to evaluate the heterogeneity, which measures the relative variability of a data set in relation to its mean value. So we have some outcomes, important outcomes regarding the type on the effect of heterogeneous reservoir. So highly reservoir heterogeneous will show a significantly low saturation with water production rate in the high heterogeneous over 200 times greater than it is in less reservoir heterogeneous reservoir. Also for for reservoir with the coefficient variation values that is less or equal to 0.25, the gas saturation and the water production remain relatively stable with the minimum variation. Reservoir with low heterogeneity experience a decline in gas saturation over time, which means that we need to avoid a long shut-in period to avoid a decrease for gas saturation. So as a conclusion for these main parameters that affect the performance of the subsurface reservoir or the subsurface part reservoir with regarding the petrophysical properties for the porosity and the permeability. So reservoir with porosity ranging from 5 to 15% to and permeability from 30 to 300 millidarcy make more adequate for the CEEGS concept, which is a variable that needs to be optimized for each specific reservoir. Another reservoir need another study. So isotropic reservoir, they are always preferable, but the influence of anisotropy is low relevant when porosity is low. However, high porosity value always negatively impact the gas saturation and the water rate. So for better candidate for a porous media scenario, it's better to look for homogeneous reservoir with the coefficient variation less than 0.25 and with the impact of the permeability on gas saturation. However, for the case of heterogeneous can be mitigated by the placement or the position of the CO2 injection point closer to the top of the reservoir. In this study, as an important outcome and as previous authors from other studies, it's preferable to have a gas saturation around 55 as a minimum saturation around the injection well to start the energy storage cycles. Thank you.
Dunya, thanks for this. It was very interesting also to see how we can implement this in the real case scenarios underground where the future lies, because we want to utilize or apply this technology all over Europe when it's developed well enough. So thanks again. And now I'm going to give the word to Aristides. He is our colleague from Greece, and he graduated at Department of Mechanical Engineering of Aristotle University in Thessaloniki in Greece in 2017. And since the beginning of last year, he is working as a research engineer at the Chemical Processing and Energy Resource Institute of the Center for Research and Technology, ELAS, and since last year, June, he's also the PhD candidate at the Department of Mechanical Engineering at the Aristotle University in Thessaloniki. His main research interests are in the fields of renewable energy systems, energy storage, energy system management, and process system engineering. So please, Aristides, the floor is yours, and pass us through your presentation. Thank you. Aristides, are you with us? Aristides?
Hello, can you hear me now?
Now we can hear you. Please.
Sorry, there was an issue with the speaker. Sorry about that. So yes, so I'm representing CERF here, and if you can move to the next slide, please. Yes, here. So we've been working at on the dynamic model and the control strategies for the CEEGS system to evaluate its dynamic performance. And at the same time, we have also been working on a digital twin of the CEEGS system. Next slide, please. So we have developed the dynamic model in Aspen HYSYS for a 1 megawatt capacity. And we have been using an operating scenario where initially the charge cycle starts, the hot water tank fills in, and once that has been accomplished, then discharge cycle is activated until the hot water tank is depleted, and then the process starts all over again. So this is a base case operating scenario that we have started with. And we have also been using 4 PI-PID controllers at 4 points to control some specific temperatures. Some initial results of this base case scenario. So compared to a model without CO2 geological storage, improvement in the dissipated energy on the thermal energy storage tanks, and improvement on the overall round trip efficiency, as you can see on the table on the right. Next slide, please. Yes, sorry about that. Yes, there. Here you have the dynamic behavior of some selected parameters like the liquid percent level, works, and mass flows. And you can notice that compared to the dust line, the system without geological storage, we have improved dynamic behavior, smoother dynamic behavior, and faster dynamics. The overall system in this scenario lasts for about 70 minutes, with 44 being the charge cycle and the rest being the discharge cycle. Next slide, please. Here you can see the digital twin we have created. Initial in terms of the architecture, the displaying of the results, the live results is happening with Node-RED. MQTT is used for streaming the data, and REST API is used for request response functionalities, while MongoDB is used for storing the data. Python was used for the overall orchestration to communicate with all the different tools. And of course, Aspen HYSYS, as we mentioned, was used for the modeling of the system. On the right, you can see the graphical user interface, which allows us for the demonstration visualization of the overall system, and also allows us to input certain parameters and take back certain KPIs and system efficiencies. For example, you can see results about the tanks, temperature, pressures, liquid percent levels, and other results like heat utilities, works, mass flows, temperatures in certain critical points of the system. Next slide, please. To conclude, what the dynamic simulation of the system allows us is to evaluate the dynamic performance, different control algorithms, and systems KPIs and critical parameters, while the digital twin allows us for the demonstration and visualization of the overall CEEGS process. In the future, we'll be working on different operating scenarios because, as I said, we have just worked on some initial base case scenarios that will integrate different renewable energy systems production profiles, thermal energy storage utilization, and integration of different subsurface storage scenarios. We'll also be working the dynamic optimization of the overall system to achieve the optimal integration of the different CEEGS subsystems and improve the overall system design. Thank you. Marco, that's it from me.
Thank you very much for this really interesting presentation, Aristides, and you've flown through very quickly because you made me realize we are quite behind the schedule. But anyhow, the topic is so interesting that we will not cut anybody's presentation. So now we go to the last part of the presentation, instrumentation and measurement of thermodynamic variables for the CEEGS demonstration loop. So Sebastian studied mechanical engineering and energy technology, and he concluded his bachelor's almost, well, 10 years ago. And 3 years ago, he received also PhD in mechanical engineering, all from the Faculty of Mechanical Science and Engineering at Technical University of Dresden. He's currently the head of the Thermal Energy Technology Group, and his research interests lie in the fields of heat transfer, energy processing, utilizing supercritical CO2, and thermal critical energy storage technologies.
Yeah, thank you for the kind introduction. I will talk on the instrumentation and measurements to get the thermodynamic variables, which were presented by the colleagues in the experimental loop we built for the project. I will show you at first the facility, then a general concept of the measurements and instrumentation. Then I go into the temperature, pressure, volume, mass flow measurements we're using and show you one application within the project. So here you can see computer-aided design of the CEEGS facility on the left-hand side, and on the right-hand side you can see some photos of the loop. Yeah, we're having a separation vessel for charging the compressor, for discharging a pump. Then there are the two main heat exchanger involved in the concept and the expansion devices. You see a part of the facility is located on the outside. Especially if we're having a huge volume of CO2 in the storage tank or separation vessel. And it's better to have a bigger volume of CO2 in the outside in case of leakage. And of course, we fill up the system with CO2 bottles. There are also some measurement devices you can see in the background here, flow measurements. And the design is made for 300 bar and 250 degrees Celsius. So first of all, when you want to build up an experiment and want to determine which measurements you want to have, you will have see on this concept, which was presented by the colleagues before, or by the partners before, and then you develop a piping and instrumentation plan, and then you determine where all the measurements are, temperature, pressure, and so on. After knowing how many and where to put them, you need to learn what is the reason to have it. Yeah, we want to measure temperature, pressures, mass flow rate, and quite often you need fluid properties of the CO2 in our case, and there are fluid or lookup tables. You can know if you know temperature and pressure, then you can know viscosity, density, and other parameters. Then you can calculate the heat transfer, the power, pressure drop, and so on. In the end, you can determine the performance of your system and of individual components involved in the process. Here's a small table of the measurements we take, and I will give you the examples for that one in the next slides. The typical principle on how something is measured is shown here. So for example, you have a temperature sensor. We're measuring a temperature here. You connect that one to a switch cabinet where all the measurements are taken. And then usually you give an electronic signal. It already looks quite electronic. So usually 420 milliampere to a process control system. There's a whole process is controlled. Organized valves are opened and closed. And before you even can measure something, you need to calibrate this whole measurement chain. So you calibrate the whole chain in order to have the correct results. You determine the frequency, so how fast you measure, one measurement per second, one measurement in 5 seconds, or 5 measurements in 1 second, and so on. And then you store and save the data. And in the end, we analyze and process the data for example, model validation. One of the most important parameter, key process parameter is temperature. Of course, also for safety, you don't want to have too high temperature. And there are many technologies, but two main technologies used. One is the resistance thermometer. You know that maybe from physics from school, Ohm law. So you can, from the voltage and the current, you can know the resistance of a sensor. And each, depending on the material, has a different characteristics. For example, here's a nickel resistant temperature characteristics. So the higher the temperature of this element, the higher is the ohmics, the resistance, and you can measure that one. There are different designs. Usually there are wires wrapped around something, they're sealed, but there are also these thin film elements where you have really long wires on a surface, and there are even micro applications. That's a measurement in centimeter. You see really tiny temperature measurements are possible. The second most used technology is the thermocouple. It's called the CEEGS effect. So whenever you have in a metal, for example, a different temperature in two directions, charge carrier will concentrate in one end. That one is used by having two different materials, the measurement in one location. Then you have a reference temperature, and out of the two different temperatures and the materials, you can know a current, voltage, and then you can determine the temperature. These are the CEEGS coefficients, which are listed for different materials here. All of that is quite standardized, standard components you can buy and install, and yeah, after calibration to be used. The second important measurement is pressure. Pressure is also really important to determine fluid properties and performance of things. Also, if you want to have vacuum, if you have afraid of overpressure, you need to measure that. Again, I will show them two mainly used sensors, which is a capacitive pressure sensor. So you have a certain material in a capacitive location, and depending on the location of this white one, you can know the capacity, and that one can be measured again, or the change of the capacity by the lens, and then you know how it is influenced. Just so a small remember from school, pressure is a force on a surface. So usually you have a force on such a surface. So how does it look like? You have, for example, a diaphragma, which is receives a certain pressure. Then you have here a reference pressure. And as this pressure is higher, you have a certain movement of that one. And then you can measure the difference in length and the influence on the capacity. Usually they're quite linear combination, as you see from the formula. So the length changes, or the movement of this diaphragma changes, and then you can measure the capacity. The other one is an inductive pressure sensor. So you use inductive change of inductive. The classical principle is a cross-anchor system where you're having two inductive generators, and then again you can measure the movement of a certain material in this field. Again, how does that look like in reality? You're having a certain pressure here. You want to measure a reference pressure here. And then there's a membrane which moves if you put pressure on it. And by the change of this ferrite core or cylinder in the core, you can measure the change on the inductive field. And then you know, can back calculate what is the pressure. Let's go to the volume and mass flow measurement. There are actually many technologies. I will only go to, I would say, the four most used principles. The most easiest one you can see here is a differential pressure flow meter. So actually you measure a difference of pressure. So example, you reduce surface area where you have flow, for example, CO2 flow through this orifier, for example. Then the velocity increases in this area, but the pressure reduces. And then you can know from the pressure difference you measure here and the pressure difference you measure here, the volume flow rate. You can back calculate it by this formula. There are some constants depending on the geometry you have here, so how you reduce the cross-sectional area. The next one is a Coriolis flow meter. So there's a Coriolis force, which means if you have a flow going in, a U-shaped tube, you flow in, you flow out, and due to this flow, you have a certain shaking. It's really minimal. It looks like really big here, but in reality, steel tubes are only shaking a tiny bit, and this shaking can be measured. So there's a force acting here, and a certain frequency, how fast it changes, swings, and then you can calculate back the mass flow rate. Special on this technology is you directly measure the mass flow rate. For all the other technologies, usually you measure volume flow rate, and you can calculate back to the mass flow rate by density. And that's how it looks in reality. The next one is a vortex flow meter. So you put a certain object into the flow, and then vortexes are generated. And they give a certain pressure on a measurement. Here you can see it like this on the back end of such an object. You measure the pressure and the force which is acting on this pressure sensor. And from that one, depending again on the geometry of this object, you can calculate the volume flow rate. Here it really depends on the range you use. There's a dimensionless number called Reynolds number, which depends on the size of a channel and the fluid and so on. And so you can operate that only in a small area of volume flow rates. The last one I want to show is an acoustic flow meter. So you are using sound waves. You emit them in a certain angle into the flow. Then you have a receiver, and the sound wave goes back to the transmitter. And depending on the flow velocity, the wavelength is changed. So you see here, it's really tiny, the difference, but that's a wavelength at the start and that's a wavelength at the end. And there's a small difference you can see here. And depending, there are different mathematic formulations how you can calculate it. But for example, with the frequency differential at a constant wavelength, you can, from the difference in the frequency you emit these sound waves, you can calculate the velocity. There are other technologies like magnetic, acoustic things, but I will not go into the details for that. In our project, we are usually using Coriolis flow meter because they're working really, really well with CO2. And on my last slide, I will give you an example. For example, how a heat exchanger can be characterized or the performance can be determined. That's one of the heat exchangers in the concept. And we have a CO2 flow from the one side to the other side. And here on this direction would be hot water flowing, but I will focus on the CO2 flow. And for example, you want to learn what's the pressure drop of the heat exchanger, or you want to know what's the thermal performance of the heat exchanger. Yeah, for the pressure drop, you have at the inlet and the outlet, you have a pressure sensor, as I was showing before with this diaphragma, for example. That was a conductive measurement of the pressure drop. For the thermal performance, you would need the mass flow rate, for example, with the Coriolis flow meter. And you would measure the temperature at the inlet and outlet, so you know the temperature difference. And CP, which is a specific heat capacity of CO2, for example, that were the lookup tables I was telling you before. So you need to know the pressure, you need to know the temperature. And from these two, you can know what is a specific heat capacity. And then you can calculate on how much the temperature increases or reduces, what is the heat transferred within this heat exchanger. That's it for my presentation, and I'm happy to answer questions. Thank you.
Thank you very much to all the presenters. Now I open the floor for your questions and comments. So please, we have quite a good number of attendees. And let's see what we already have one question. So Edgar is asking, what is the necessary well spacing and time frame for the CO2 plumb to reach the producer's well, ensuring the project remains attractive from a practical perspective? Who's going to answer that one?
I think it's me. The question is for... can you please repeat, Marco, the question?
Yes. Okay. What is the necessary well spacing and time frame for the CO2 plume to reach the producer well, ensuring the project remains attractive from a practical perspective?
Mm-hmm. So in our scenario, the concept or the of our system is like the producer, the injector well is being the injector for the plume setup, and it is the same well for the back producer for CO2. So it is the injector and the producer as well. But from practical for practical application, we can have another scenario, which is another well B that can, where we can inject CO2 and then produce from another well at a certain distance. This scenario has been simulated, and the minimum for our specific case, the minimum distance from CO2 for perspective of CO2 gas saturation is less than 400 meters, and for perspective for the temperature, because the temperature is very important, as the CO2 is like less than 150 meters to avoid to let for the temperature to be equilibrated with the formation, and to have enough high temperature for the wellhead back producer CO2.
Thank you, Dunya. I hope this answered the question provided or given to us. If not, you can again pose your questions in the question and answer section. Are there any other questions? I don't see any. I would then just ask Ricardo, as being the coordinator of the project. We have still some time, and I think I can allow myself posing this question. So what, up from the results, from the current results within the project, do you see the biggest challenges that we need to address in the forthcoming year, and maybe also beyond the project, if there will be a possibility? Thanks.
Okay, thank you, Marco. So, a good question. So probably because we have already discussed a lot about it, about the next steps. The good thing of the concept that we are studying, that we are developing, is that most of the components and the knowledge required for the successful development is already available for the heat exchangers, the compressors, for the wells. So we have a real, we have an advantage because we share technologies with the power sector, but also with the geothermal sector. So we have a good pathway already advanced. So the challenge is, the main challenge that we identify is in the interface. How the system, the global system operation will be affected by the charging and discharging condition variable, and with the presence of impurities as chemicals, as particles. That's on the side of the surface components. And on the side of the geological part, we have a very, let's say, a strange, novel application. We are considering porous media and salt cavities and other configurations, but we are having charging as discharging cycles that instead of having long periods of oscillation, they have, for the geological approach, fast oscillations. So we have, on one hand, first to demonstrate that the purity or that the outflow of the wells are clean enough for a correct performance and then for a long period operation. At this stage, with all the simulations and all the analysis that we are performing are relatively good, quite successful, so we expect that it won't be a problem, but it must be demonstrated under real operation. On the other side, at the part of the wells, at the part of underground, we need to advance in the specific knowledge required for the fast charge and discharge. When I say fast, is compared to the typical geological times, typical application of geological storage time. So, but going to the second question, the results that we have obtained until now, they are pretty successful. I would say that in these 2 years, we have already reached the successful results, and we can say that the concept is technology is viable, that the technology is feasible, and the relatively good efficiencies, round-trip efficiencies are reached, that the components works with adequate configurations can work pretty good. At this moment, everything that is quite smooth for going to a second step in which a real system operating for a period, a representative period, demonstrates or shows new issues to appear. But at this moment, I'm pretty optimistic regarding the future of the technology from the point of view of the academia, from the point of view of the analysis, from the point of our numbers looks quite nice. Now the companies must see if they think that is worth to bet on this technology or in others. I don't know if I answered
Thanks, Ricardo. I think you did, and you passed the ball to the application part of the domain, so technology, industry, and end users. We'll see how many of them will be attracted by this. I'm sure that we will get some interest in the future, and quite positive that this could be developed further on. I see no other questions, and we are roughly on time, I would say a little bit over. So we spent the time that was dedicated to this workshop quite well. And with this, Ricardo, if you allow me, if you don't have anything to add, I would conclude the workshop. I would again thank sincerely to all the presenters, and of course to all the participants that followed this workshop. And please do not forget, this recording is going to be available on the CEEGS webpage for quite some time. Please pass the information further if anybody else would be interested to see it later on. Thank you very much, and have a successful remaining of the day and the week. Enjoy it.
Okay, thank
Bye
you
bye.
very much. Bye.